Welcome back. This will be part C of a video lecture on section 3.5, subspaces, basis, dimension, and rank. In part A, we covered the concept of a subspace, and we looked at some subspaces associated with matrices. In part B, we covered the topic of basis. Here in part C, we'll take up dimension and rank and coordinates. So let's begin with dimension and rank. Now let's begin by looking at the following problem. Let's find a basis for the collection of vectors spanned by the three vectors that you see in front of you, and let's do that in two different ways. So join me at the document camera for the solution to this problem. All right, welcome back to the document camera. In this problem, we're supposed to produce a basis for this subspace S in two different ways. Now I will show you how we can do this using our so-called row method, and then I'll show you how we can do this using our column method. And this will produce two very different bases for the subspace S. So our first method is to take the vectors as they're given to us and feed them in as the rows of a matrix. So our matrix will consist of the rows 1, 2, 0, 2, 5, -1, and -3, -5, -1. Now we're going to row reduce this matrix. We'll go through a sequence of elementary row operations, and we'll put this matrix into its reduced row echelon form. Now I've done this, and the reduced row echelon form consists of the first row 1, 0, 2, the second row is 0, 1, -1, and the third row consists entirely of zeros. Now according to the row method, we can throw away the row of zeros, and we can use the two remaining non-zero rows, right? Those two non-zero rows will form a basis for the subspace S. Okay, so we can think of our first basis that we're generating is going to consist of the vector 1, 0, 2 and the vector 0, 1, -1. All right. Now our next method is to take these vectors and feed them in as the columns of a matrix. This is our so-called column method. So I'll take 1, 2, 0, 2, 5, -1, and -3, -5, -1. I'll go through the sequence of elementary row operations, and I'll reduce this now down to its reduced row echelon form. And this will consist of 1, 0, -5, 0, 1, 1, and 0, 0, 0. Now here our interpretation is different, right? We're not going to find the basis of vectors over here. What we are going to notice, though, is that there's a leading 1 in column 1, and there's a leading 1 in column 2 of the reduced row echelon form, and that will direct us to go to those very same columns in the original matrix and identify those as the basis vectors for our subspace S. So our second basis is going to consist of 1, 2, 0, 2, 5, -1. Okay? So what's interesting here, and this is what we have to kind of take with us as we move forward, is that it's obviously very possible to take a subspace and represent it, produce different bases for that subspace. So we found one basis using a row method. We found another basis for S using a column method. So we found two very different bases for the subspace S. But what's interesting is that in both cases, the size of the basis consisted of two vectors. And what our next theorem is going to tell us is that no matter how we would try to construct a basis for S, it would always consist of two vectors. So let's go back to the class notes and look at that theorem. Here's theorem 3.23, the basis theorem. Let S be a subspace of Rn, then any two bases for S have the same number of vectors. Let's look at the proof of this important theorem at the document camera. All right, welcome to the document camera. Let's look at the proof of theorem 3.23. And what I'm going to show you is a special case. And I think once you see the special case, you'll see how to handle the general case. Let's assume that S is a subspace of Rn, and let's imagine that S has two different bases, right? One is called B1, which consists of two vectors, and another is called B2, which consists of three vectors. What I want to show you is that this will always lead to a contradiction. The fact that I've got a basis of two vectors will show us that we can never have a basis consisting of three vectors, right? Let me show you how we arrive at that contradiction. Now, the way to get things started is just to realize that each one of these vectors, v1, v2, and v3, is an element of S and is therefore expressible as a linear combination of u1 and u2. So here we're using the fact that u1 and u2 span S, and therefore each of these three vectors is expressible in terms of u1 and u2. So we end up with these equations. We can write v1, for example, is going to be some combination of u1 and u2. Let's say a1 u1 plus a2 u2. v2 will be, let's say, b1 times u1 plus b2 times u2. And then finally, v3 will be c1 u1 plus c2 u2. All right, so we're using the spanning property of u1 and u2 to our advantage here to write v1, v2, and v3 in terms of u1 and u2. Now, what we're going to look for are possible solutions to this homogeneous equation. So are there alpha, beta, and gamma, a linear combination of v1, v2, and v3 that could equal the zero vector? Right, so we know that there's the trivial solution is always a possibility, but are there other solutions other than simply the trivial solution, alpha equals beta equals gamma equals 0? Now what we can do if we're examining this equation is we can go in and substitute for v1, v2, and v3. And so we can get an equation involving the vectors u1 and u2. So it would look like this. I'd have alpha, and then in place of v1 I'll write a1 u1 and a2 u2. Then I'll have beta, and in place of v2 I'll write b1 u1 plus b2 u2. Then I'll have gamma, and in place of v3 I'll have this c1 u1 plus c2 u2, and this is equal to the zero vector. Now all I'm going to do, I realize everything on the left-hand side here can be written as a combination of u1 and u2. Those are the only vectors we have left. So what I'm going to do is distribute the alpha, distribute the beta, and distribute the gamma, and I'll collect terms. I'll collect the u1 terms and the u2 terms, and then I'll factor out the u1 and the u2. So I'll be left with an expression like this. I'll have alpha a1. I'm going to have a beta b1. And I'll have a gamma c1. And this will be multiplying the vector u1. And then I'll have an alpha a2, a beta b2, and a gamma c2. And this will be multiplying u2. Okay, so now we're going to use the other part of a basis, right? We know that u1 and u2 form a basis for S. We've already used the spanning property. Now we're going to use the linear independence of u1 and u2. Since u1 and u2 are independent vectors, the only way that this combination of u1 and u2 can equal the zero vector is if these coefficients are both equal to 0. Only the trivial solution is maintained here in this equation. So we know that this coefficient and this coefficient must be simultaneously equal to 0. So this tells us that alpha a1 plus beta b1 plus gamma c1 must equal 0, and alpha a2 plus beta b2 plus gamma c2 must equal 0. Now what we can do is we can look at this as a homogeneous equation in the unknowns alpha, beta, and gamma. All right, and so we can put this into an augmented matrix and treat it in this fashion, right? And we can think of the coefficient matrix as A1, B1, and C1. A2, B2, and C2. And we can think of our unknowns, our columns being given by alpha, beta, and gamma. So we have this equivalent augmented matrix that is representing our system of equations. Now, what do we know? We know that this is a homogeneous system, so we know that there's always a solution. I can always choose alpha, beta, and gamma equal to 0. So we always know that there is a solution. The question now is there necessarily a unique solution, or are there infinitely many solutions? Well, I claim in this case we know that there are infinitely many solutions, and that's because there are only 2 rows, and that means we can have at most 2 leading ones. And that means that one of these columns will not have a leading one. One of these columns will be a free variable. So we know that there's a solution. That's because the system is homogeneous, and there exists a free variable. Therefore, there are infinitely many solutions. In the variables alpha, beta, and gamma. Now, in particular, what that means, let's go back to where the story began. It began back here with this homogeneous equation. What we're saying is that there are infinitely many choices of alpha, beta, and gamma that make this left-hand side equal to the 0 vector. And what that means is that v1, v2, and v3 are linearly dependent. Okay. In particular, what that means is that they're not a basis. I'll just say it this way. B2 is not a basis. Okay. So anytime, and you can generalize this. I just picked on 2 vectors and 3 vectors. You could have 3 vectors and 5 vectors, or you could have 6 vectors and 8 vectors. As soon as you assert that there's a basis that's bigger than a given basis, all right? So as soon as you have one basis and you're asserting the existence of a bigger basis, you can always show that there's a contradiction, that these vectors, in fact, cannot be linearly independent. They must be linearly dependent. And it's always going to come down to an exercise in recognizing that some matrix has too few rows and too many variables, and will therefore have infinitely many solutions. Okay, so that's what's at the heart of the proof of theorem 3.23, the basis theorem. And this is a very important theorem for making further progress in this section. So let's go back to the class notes and see how we can make immediate use of this basis theorem. Now, the basis theorem says something very powerful. It says, anytime I find a basis for a subspace of Rn, it's going to have the same number of vectors. Now, we can turn that around and call that number the dimension of the subspace. So if S is a subspace of Rn, then the number of vectors in a basis for S, in fact, for any basis for S, is called the dimension of S, and it's denoted by the symbol dim of S. So if you want to find the dimension of a subspace, all you have to do is find a basis, any basis for that subspace, and count the number of vectors in that basis. That number will be the dimension of S. Now let's put this concept to use. Let's look at theorem 3.24, and this is telling us something very important about a matrix. The row and column spaces of a matrix A have the same dimension. Let's go to the document camera and look at a proof of theorem 3.24. Welcome to the document camera. We're going to look at the proof of theorem 3.24. Now, instead of working with a general matrix, I'm going to work with this explicit matrix. And what we're going to do is work out the dimension of the row space and the dimension of the column space. We'll see that they're equal And we'll see the underlying principle is, we'll understand why for any matrix, why these would have to be equal. We'll just study this explicit example. This will reveal the general principle, and it will be easier to work with these explicit numbers. Now, let's work out the row space first. Let's work out a basis and therefore the dimension of the row space. So what are we going to do? To get the dimension or to get a basis for the row space, we're going to first put this matrix in its reduced row echelon form. So we're going to go through a sequence of elementary row operations. I've already done this, so I can show you the result, but there's a sequence of elementary row operations that will ensue, and we'll end up with a reduced row echelon form consisting of, the first row will be 1, -1, 0, and -2. The second row will consist of 0, 0, 1, and -3. And the final two rows consist entirely of zeros. Okay? Now, from the point of view of working out the row space, the basis for the row space, our previous work shows us that all we have to do is take this row and this row from the reduced row echelon form. I can skip these last two rows because they consist entirely of zeros. These two rows are going to form the basis for the row space. So our row space, the basis for the rows, will consist of 1, -1, 0, and -2, and 0, 0, 1, and -3. In particular, that shows that the dimension of the row space of the matrix is equal to 2. And if we were looking for a general principle to extract from this, we would say, well, after you do the row reduction, you can throw away all the rows consisting entirely of zeros and only keep the rows that are non-zero. But one thing to notice is that every row that's not zero is associated with a leading 1. So in fact, this 2 is really counting the number of leading 1s that persist in this reduced row echelon form. Okay, that's looking at the row problem. Now let's think about this as the column problem. Now we've got this set of columns, and we're looking for a basis for the span of the columns. In other words, a basis for the column space of A. Now, the first step is exactly the same, right? We go and we put the matrix through a sequence of elementary row operations. We put the matrix into reduced row echelon form. So we do this move. Now our interpretation of this reduced row echelon form is different. In this case, we look for the columns that contain the leading 1s, and we go back to the original matrix and we take those columns as the basis for the column space. So here we see that there's a leading 1 in column 1, and we see that there's a leading 1 in column 3. And so we go back to the original matrix and we grab column 1 and we grab column 3, and we say that a basis for the column space is going to consist of 5, 2, -1, and 4, and 0, -3, 2, and 3. The dimension of the column space of A is therefore equal to 2 because we have a basis of size 2. Now, if you're again trying to extract a general principle of this, what would you do? You'd take your general matrix A, you'd row reduce it, and you'd look for the columns that contain the leading 1s, and you'd refer back to the original matrix and grab those associated columns. But the point is that number 2 is completely explainable, therefore, by the total number of leading 1s in the row reduced echelon form. So what we're seeing here, the general principle that's at play here, is that the reason why the row and the column space, the reason why they have the same dimensions is because they're both referring to exactly the same thing, the number of leading 1s. From one point of view, we're looking for the rows that contain the leading 1s, and from the other point of view, we're looking for the columns associated with the columns that contain the leading 1s. So the fact that the dimension of the row space and the dimension of the column space are equal to each other is really just pointing to that fact that they're both counting the number of leading 1s in the row reduced echelon form. And so that's the general principle that's governing the proof of theorem 3.24. All right, let's go back to the class notes and continue. Due to theorem 3.24, we can now make the following definition. The rank of a matrix A is the dimension of its row and column spaces and is denoted by rank of A. Now, back in chapter 2, we encountered the definition of rank in a slightly different context. There we said the rank of a matrix is the number of non-zero rows in its row echelon form. And now, from our work in looking at theorem 3.24, we can reconcile these two definitions and see that they amount to the same thing. Let's look at theorem 3.25. For any matrix A, the rank of A transpose is equal to the rank of A. And this theorem follows very easily from the duality of a matrix and its transpose. In other words, the rows of a matrix become the columns of the transpose, and the columns of the matrix become the rows of the transpose. So, when we want to think about the rank of A transpose, one way to think about that is it's the dimension of the row space of A transpose. But the row space of A transpose is the column space of the matrix A. So that's equal to the dimension of the column space of A, but that is, by definition, the rank of A. So the rank of A transpose equals the rank of A. So as we've seen, the rank of a matrix A is a very important number associated with a matrix. It can be thought of as the dimension of the row space of A, or it can be thought of as the dimension of the column space of A. Now, here's another very important number associated with a matrix. This is called the nullity. The nullity of a matrix A is the dimension of its null space and is denoted by nullity of A. Now let's work an example that brings all of these concepts together. So in this problem, I want us to find the rank and the nullity of the matrix A. So join me at the document camera to put all of this together. Welcome to the document camera. In this problem, we're going to work out the rank and the nullity of this matrix A. Now we know that the rank is either, we can think of it as the dimension of the column space or the dimension of the row space, since they're equal to each other. And the nullity, if you recall, is the dimension of the null space of the matrix A. So let's begin with the nullity. We want to find the dimension of the null space of A. And if we're thinking about the null space of A, of course, we're looking at the subspace of all vectors x that satisfy this homogeneous equation. And if we were going to find a basis for this subspace, we would begin by taking this as the matrix of coefficients. Augmenting about a column of zeros, and then row reducing. We would get this into its reduced row echelon form. Now in this case, I've done the work and I can show you what the reduced row echelon form looks like. We're going to have a row of 1, -1, 0, -3, and 4, and 0, 0, 1, -2, -1, 0. Now, if we were going to try to express all the solutions to this system of equations, we'd want to classify our variables into the type that are bound and into the type that are free. We would easily identify the bound variables by the ones that have the leading ones in them. So we would declare this variable bound and this variable bound, and all the others would be called free variables. Now, if we were asked to produce a basis for the null space, we'd have to continue to work with this system of equations and write out all of the system of equations. But we know this. Without writing out an explicit basis for the null space of A, we know that we're going to get a basis vector, right? One for each of the free variables that are present. So without explicitly writing out the basis for the null space, we know that there will be 3 vectors in that basis. And so without doing any further work, we can declare that the dimension of the null space of A, the nullity, if you will, is equal to the number of free variables, which in this case is 3. Okay, now let's think about how we would find the rank, which is either the dimension of the column space or the dimension of the row space. What we would do is we'd take the matrix A, we would row reduce it, and one way to think about the dimension of the row space is just to grab the two vectors that remain here, right? We're going to have two vectors, one for this row with the leading 1 and another one for this row with the leading 1. These two rows will form a basis for the row space, and so the dimension of the row space is simply 2. So in this case, the rank, which in this case we're thinking about as the dimension of the row space, is going to be 2. Basically, we're getting 1 for each of the leading variables, so this would be the number of leading variables or the number of bound variables, which in this case is equal to 2. 1 for each of those leading ones. And so there's our calculation. The rank is equal to 2, and the nullity is equal to 3. Now what we notice in this example, and we will look to generalize this, is that the sum of these two is always going to have to equal the number of variables. The sum of the nullity and the rank will always equal the number of variables, which is equivalent to the number of columns. And so when we look at this matrix and identify it as having 2 rows and 5 columns, we knew already just by the dimension, right, the number of columns of this matrix, that the nullity and the rank together would have to equal 5. Okay, so let's go back to the class notes and talk about that phenomenon. Theorem 3.26, the rank theorem, is merely a generalization of the results of our previous exercise. The rank theorem says this: if A is an m by n matrix, then the rank of A plus the nullity of A must equal n. We are now ready to state and prove Theorem 3.27, the fundamental theorem of invertible matrices, version 2. Now, throughout this theorem, A is going to be an n by n matrix. And in this theorem, we're presented with 13 different statements about the matrix A. And what the theorem is telling us is that if any one of them is true, then all of them are true. Now, the first 5 of these we've met before. We saw them in version 1 of this theorem. So let's remind ourselves of what the first 5 statements of this theorem are saying. So statement A says that the matrix A is invertible. And statement B says that the equation AX equals B has a unique solution for every B in Rn. Statement C says that the homogeneous equation AX equals 0 has only the trivial solution. Statement D says that the reduced row echelon form of A is the identity matrix. And finally, statement E says that A is a product of elementary matrices. Now, what we showed in version 1 of this theorem is that these 5 statements are equivalent. Knowing that any one of them is true proves or gives us the truth of all of them. Now, what we're going to do is add on 8 additional statements, F through M. Now, these 8 statements are of a different kind than the first 5. We might say that these first 5 statements are all of an algebraic nature. They're all saying something algebraic about the matrix A. In contrast, these remaining 8 statements are saying something geometric. They're saying something about spanning and independence and basis and dimension. So what we're seeing here in version 2 of this theorem is a merging of the algebraic properties of the matrix A and its geometric properties. So let's take a look at these remaining 8 statements. Statement F says that the rank of the matrix A is equal to n. Statement G says the nullity of A is equal to 0. H says that the column vectors of A are linearly independent. Statement I says the column vectors of A span all of Rn. Statement J says that the column vectors of A form a basis for Rn. Statement K says that the row vectors of A are linearly independent. Statement L says that the row vectors of A span Rn. And finally, statement M says that the row vectors of A form a basis for Rn. Now, what I want us to do is go over to the document camera and give a proof of Theorem 3.27, the fundamental theorem of invertible matrices, version 2. So join me at the document camera for the proof of this theorem. Welcome to the document camera. This will be our proof of Theorem 3.27, the fundamental theorem of invertible matrices, version 2. Now, we will demonstrate the equivalence of statements A through J, and we will address statements K, L, and M at the very end of this proof. Now, this diagram contains statements A through J. Statements A through E are on the outside cycle, colored in red, and we encountered these statements in version 1 of this theorem. So we know that if any one of these statements is true, then all of them are true. Statements F through J are listed on the inside of this cycle, and our task is to show that we can add these internal 5 statements to the list of equivalence statements. I will show you how we can link these statements together using these arrows to indicate implication. So once we've established these implication arrows, then the theorem will follow. So for example, if we know that A can be expressed as a product of elementary matrices, then we can follow our diagram and come to the conclusion that the columns of A form a basis for Rn. First, let's study these blue arrows. If the columns of A form a basis for Rn, then obviously the columns of A are linearly independent and the columns of A span Rn. That follows directly from the definition of a basis. Now let's study these green arrows here. By the rank theorem, we know that the rank of A and the nullity of A have to add up to n. So if the rank of A is equal to n, that's absolutely equivalent to saying that the nullity of A is equal to 0. On the other hand, we know that the rank and the nullity of the matrix A can be referred to the reduced row echelon form of the matrix A. So to say that the rank of A is equal to n is absolutely equivalent to saying that the matrix A is row reducible to the identity matrix, since each row of the reduced row echelon form of A must contain a leading 1. And likewise, to say that the nullity of A is equal to 0 says that the reduced row echelon form of A is the identity matrix, since each column of the reduced row echelon form must contain a leading 1. Let's look at this green implication arrow here. The matrix product A times X, the matrix A times the column vector X, can always be realized as a linear combination of the columns of A. So to say that A times X has only the trivial solution is absolutely equivalent to saying that the columns of A are linearly independent. These two statements are saying exactly the same thing, albeit in slightly different language. Next, let's talk about the two pink implication arrows that we see here. And let's begin with this one first. So once again, the matrix product A times X, the matrix A times this column vector X, that can always be rendered as a linear combination of the columns of A. Thus, AX equals B has a unique solution implies that the columns of A span Rn. Given any vector B in Rn, I can find a linear combination of the columns of A that equals B. That's equivalent to saying that the columns of A span Rn, and that's what accounts for this first pink implication arrow. Next, let's study this longer pink implication arrow, and this is going to require us to stack a few ideas together. And let's begin by noticing that each column of the matrix A is a vector in Rn, so that the column space of the matrix A is a subspace of Rn. On the other hand, we're being told in this statement that the columns of A span Rn, and that means that the column space of A must include all of Rn. In other words, every vector in Rn is expressible as a linear combination of the columns of A. Putting these two ideas together, we see that the column space of A must equal Rn. All right, so that's idea one. Now, the dimension of the column space of A is therefore equal to the dimension of Rn. On the other hand, the dimension of Rn is clearly equal to n because I can find a very simple basis for Rn, namely the n standard unit vectors. And since those n standard unit vectors form a basis for Rn, the dimension of Rn is simply n. So we're being told that the dimension of the column space of A is equal to n. But another name for the dimension of the column space of A is the rank of A. So we're able to conclude that the rank of the matrix A is equal to n. In other words, knowing that the columns of A span Rn allows us to conclude that the rank of the matrix A must be equal to n. And that's exactly what this longer pink arrow is asserting. So that's how we show the longer pink implication arrow here. Now, if we stopped our argument here, we would not quite be done. Since the columns of A form a basis for Rn, would have no arrow directed into it. In other words, there'd be no way of knowing that if A is invertible, that the columns of A form a basis for Rn would be true. And so we're going to remedy this by showing the existence of this yellow implication arrow. We're going to show that if we know that the columns of A span Rn, then we in fact know that the columns of A form a basis for Rn. And here's how the argument's going to go. We know that if the columns of A span Rn, then the rank of A is equal to n. We've already proven that implication arrow. We know that that's equivalent to saying that A is row reducible to the identity matrix, which is equivalent to AX equals 0 has only the trivial solution, which is equivalent to saying that the columns of A are linearly independent. So knowing that the columns of A span Rn also implies that the columns of A are linearly independent. And those two statements together imply that the columns of A form a basis for Rn. So in fact, we do have the existence of this gold implication arrow linking the columns of A span Rn with the columns of A form a basis for Rn. And so that completes the link. And now we know that if any one of these statements is true, then all of them are true. So finally, we must address statements K, L, and M. Now these statements K, L, and M mirror the statements in these gray boxes with the word column replaced by the word row. So for example, one of the statements which mirrors this one says that the rows of A span Rn. Now I'll show you this example, but you can do the same thing with the other examples. I'll show you that this statement here, that the rows of A span Rn, is completely equivalent to the statement that the columns of A span Rn. Now, in order to prove this, we're going to have to stack a few ideas again. So let's begin with the rows of A span Rn. Now, since the rows of A are the columns of the transpose of A, this statement is absolutely equivalent to the columns of A transpose span Rn. Now, at this point, what I want you to imagine is, since A is an n by n matrix, so is A transpose. A transpose is an n by n matrix. So what you temporarily have to do is you have to take this whole diagram, and everywhere you see the matrix A, you have to put the matrix A transpose. But basically what we have is that the columns of A transpose span Rn. So once we know that that's true, we can go down and follow this pink arrow and know that that's absolutely equivalent to the rank of A transpose equals n. These two statements are absolutely equivalent now, phrased in terms of the transpose rather than the matrix A. So the columns of A transpose span Rn is completely equivalent to, based on our work, the rank of A transpose equals n. But as we showed in a previous theorem, the rank of A transpose is equal to the rank of A. And so this statement is equivalent to the rank of A is equal to n. And as we know from our previous work, the rank of A equaling n is equivalent to the columns of A span Rn. So the rows of A span Rn is equivalent to the columns of A span Rn. And so we have the equivalence between these two. And therefore we know that if this one is true, then any of the other statements are true as well. And if any of these other statements are true, then we know that the rows of A span Rn. So we've been able to pull this statement into our diagram, and there will be an equivalent proof to show that each of the mirror statements for these other two statements in gray boxes, the statements where we replace columns by rows, can also be pulled into this diagram. And this completes our proof of Theorem 3.27, the fundamental theorem of invertible matrices, part 2 or version 2. I hope you've enjoyed our proof. Let's go back to the class notes. Our next topic is coordinates. Now, up till now, we've been specifying a vector in n-dimensional space through its components, which we can think of as specifying the vector relative to the standard unit vectors, a standard basis for n-dimensional space. Now, in many contexts, we'll be working within a subspace of n-dimensional space, and within that subspace, we'll have some basis. And it seems natural, therefore, to specify that vector relative to the basis of that subspace. Now, our next theorem, Theorem 3.29, is a crucial step towards defining the coordinates of a vector relative to a basis. So, let S be a subspace of n-dimensional space, and let script B be a collection of vectors v1 through vk that form a basis for that subspace S. For every vector v in S, there is exactly one way to write v as a linear combination of the basis vectors in script B. Now, let's go to the document camera and look at the proof of Theorem 3.29. All right, welcome to the document camera. We're going to prove Theorem 3.29. Let's just remember that S is a subspace of Rn. B, consisting of the vectors v1 through vk, is a basis for S, and that V is just a generic element of the subspace. Now, we know from the spanning property of a basis that V is expressible as a linear combination of the vectors v1 through vk, in this case with coefficients c1 through ck. Now, what we want to assume is that V is perhaps expressible as a linear combination of these same vectors, now with possibly different coefficients, with possibly different scalars, in this case gamma 1 through gamma k. Let's see what follows from this assumption that there are two different representations for the vector v in terms of that basis. All right, what I'm going to do is take the difference on the left-hand sides and on the right-hand sides. So when I take the difference on the left-hand sides, I get v minus v, or the zero vector. And on the right-hand side, I'm going to get the difference between these vectors. What I can do now is group them. I can put the v1s together, the v2s together, and the vk's together and factor out v1, v2 up through vk. I can express the difference on the right-hand sides as c1 minus gamma 1 times v1, c2 minus gamma 2 times v2, on out to ck minus gamma k times vk. All right, now what I have here on the right-hand side is a linear combination of the vectors v1 through vk. Now I'm going to use the linear independence property of this basis. I have a linear combination of the vectors v1 through vk, which is equal to the zero vector, and that means that all of these coefficients, all of these scalars, must be equal to 0. So as a consequence of the linear independence, C1 minus gamma 1 is equal to 0. And C2 minus gamma 2 is equal to 0. And this will go on out to CK minus gamma K is equal to 0. Now, that of course means that C1 is equal to gamma 1, that C2 is equal to gamma 2, and that CK is equal to gamma K. So in other words, I really don't have two different representations for the vector v. C1 and gamma 1 are the same, C2 and gamma 2 are the same, on out to CK and gamma K are the same. In other words, this is the same representation, all right? And that proves that whenever I have a representation of the vector v, when I have a representation of the vector v in terms of the basis v1 through vk, that the choice of these scalars c1 through ck is unique, that there is only one way to write the vector v in terms of the basis vectors v1 through vk, and that's through a particular choice of scalars c1 through ck. All right, that's the content of theorem 3.29, and I hope you enjoyed that proof. Let's go back to the course notes and put this to use. We are now ready to define the coordinates of a vector with respect to a basis. So let S be a subspace of Rn, and let script B be a basis for that subspace. Let's say for the sake of argument that B consists of the k vectors v1 up through vk. Now let V be any vector in the subspace S. Now we can express V as a linear combination of the basis vectors. So let's say that V equals C1 times V1 plus C2 times V2 up through CK times VK. Now these scalars, C1 through CK, those scalars are called the coordinates of V with respect to the basis B. Now here's the notation we're going to use. When we take our vector V and wrap it with a pair of square brackets and then put a subscript B on it, we're asking for the coordinates of V relative to the basis B. And what we're going to give is a column vector consisting of those scalars C1 through CK. That column vector we'll think of as the coordinates of V with respect to the basis B. Now let's think about the sense of this definition. This definition is asserting that there's an equivalence between this vector V that sits within our subspace and this column of scalars C1 through CK, and this is relative to a particular basis for the subspace. So let's think about why this definition seems proper. Now, if I hand you a vector V in the subspace, Theorem 3.29 tells us that there's one and only one way to write V as a linear combination of the basis vectors v1 through vk, and that's to use these specific scalars c1, c2, up through ck. So once I hand you a vector in my subspace, and I hand you a basis for that subspace, this set of scalars c1 through ck is unique to that vector v. So this vector v has a unique representation in terms of this column of scalars c1 through ck. On the other hand, if you know the basis B and you have this column of scalars, it's very easy to recover the vector V by simply forming the linear combination, taking those scalars C1 through CK and combining them with the vectors V1 through VK. So what this definition is drawing our attention to is the equivalence between that vector V sitting in that subspace S given by this basis script B and the set of scalars C1 through CK that would come about by writing V as a linear combination of those basis vectors V1 through VK. It's drawing our attention to the equivalence between this vector V and that column of scalars. Now let's try a problem. Let U be the vector 1, 3, 1, and let V be the vector 2, negative 1, 3, and let S be the subspace spanned by U and V. Let's first show that B, consisting of the vectors U and V, is a basis for S. Then let's show that the vector w consisting of 1, 17, and -1 is an element of the subspace. And then finally, let's find the coordinates of w relative to b. All right, welcome back to the document camera. We're going to look at the solution to this problem. Let's just remember our vectors u and v have been given to us. These are both vectors in R3. U has components 1, 3, 1, and v has components 2, -1, and 3. We're forming a subspace of R3 by looking at the collection of all linear combinations of u and v, in other words, the span of u and v. Now, in this first part, we're just trying to confirm that these two vectors form a basis for S. And since the two vectors are already spanning S by definition, all we have to do is check to see that they are linearly independent. Now, we can do that in several ways, but one way is just to feed these vectors into a matrix as its columns. And then look at the reduced row echelon form. All right, so there's a sequence of elementary row operations that will bring this down to its reduced row echelon form. And when I did this, I found that I got the rows 1, 0, 0, 1, and 0, 0. And since each of these columns contains a leading 1, these two vectors are, in fact, linearly independent, and therefore, they will form a basis for S. So let's call this basis B. And let's put the basis, we'll need this for later on in the problem. Make sure we think of this basis as U first and V second. So script B, U first, V second, is a basis for the subspace S. Okay, now part B of this problem asks us to show that the vector W with components 1, 17, and -1 is an element of S. And that means we have to find some scalars, let's say A and B, such that A times U plus B times V is equal to W. Now this is equivalent to solving this augmented system. I'm going to feed in the vector U, the vector V. This will be the coefficient matrix for my system, and I'll feed in the vector W as the column of constants. And then I'll look at the reduced row echelon form of this augmented system. Now, when you do that, I've done this work. There's a sequence of elementary row operations that you can perform that will bring this to 1, 0, 0, 1, 0, 0, and 5, -2, 0. So the system's consistent. There's nothing inconsistent with that row. Our columns are going to correspond to the coefficients A and B. And so we can see right out of this that A is equal to 5 and B is equal to -2. Okay. Now our theorem, the theorem that we just worked on, told us that there was only going to be, since this is a basis, there was only going to be one choice of A and B that would make this work, right? And we're seeing that in this system, that unique choice of A and B is A equals 5 and B equals -2, right? So 5 times U plus a -2 times V is the only combination of U and V that was going to produce the vector W, okay? Now, finally, when we come to part 3, we want to express W now. We want to express its coordinates relative to this basis. Now, we do have to understand that implied in this is that the basis vectors have been given to us in a certain order. So we're going to think of U first and V second here. So when we write the coordinates of W relative to the basis B, okay, U first, V second, that we'll use the combination that we just found, and we're going to say it's 5 times U and a -2 times V. So the coordinates of W with respect to B are 5 and -2. If I inverted the order of the basis and I had v first and u second, then I would just invert these coordinates. I'd write -2, 5. So the ordering of the basis will give us the ordering of these coordinates. Okay, so that's how these coordinates can be found and how they can be listed. I hope you enjoyed the solution to that problem. And that brings a close to this section 3.5.